Hi, my name is Gabe, I'm a mathematician and a tutor, and I'm excited to dive into some statistics with you. Today's topic is discrete random variables. We will start this video by discussing random variables in general and how they are used to talk about probabilistic events. We will then discuss the specific case of discrete random variables. Finally, we will discuss some specific properties of discrete random variables. As we get ready to discuss these discrete random variables, we need to think about why random variables are needed at all. It seems like it's possible to say that a coin flip is going to be 50-50 without talking about variables, so what's the point? In short, random variables mathematically connect probabilistic events to numerical values. We model events as draws of a random variable with a certain underlying pattern or probability distribution. Crucially, random variables provide a way for us to talk about all types of random circumstances using a unified mathematical language. This means that we can talk about the outcomes of the roll of a die and how long you have to wait for a bus using the same general structures. In general, when the results of an event are restricted to a limited set of countably distinct variables, such as the possible values that you can roll on a die, we refer to that as a discrete random variable. If an event can lead to an uncountable number of outcomes across some interval, such as your random waiting time, which can be anything from no time at all to however long the gap between two buses is, we model that event with a continuous random variable. This video will focus on discrete random variables. Definitionally, a discrete random variable is a random variable that can take on a value from a countable list of distinct values. More examples of discrete variables include the outcome of the roll of a die, which only has 6 options, or how many times you would have to flip a coin before it comes up tails. Sure, it has a 50% chance of happening on any single toss, but there is no guarantee that it will happen by your first, second, third, 10th, or even 1,000,000th toss. Because we can individually list out and count the number of possible tosses, this is still a discrete event, even though there are infinitely many possible outcomes. From this understanding, how can we connect these discrete outcomes to probabilities? Discrete random variables map probability values for any given exact outcome to a number between 0 and 1. This provides the general framework for how we connect discrete random variables and probabilities. So now let's look at the exact mathematical language that we use to describe these variables. In general, we denote any random variable as a capital Latin letter, most frequently x. The numerical representation for the outcome of the event is generally written as k. Sometimes this can require us to assign numerical values to an otherwise non-numeric outcome. For example, we might switch between saying that the outcome of a coin flip is heads or tails to saying that it can take on the values of 0 and 1. The probability of some outcome k is generally written as the probability of x equal to k, but when the context is clear, this will sometimes just be written as the probability of k. Now we need to discuss the ways that we connect the random variable to probabilities. A probability distribution function connects the possible outcomes of a random variable to probabilities between 0 and 1. Discrete probability functions must follow 2 rules. Given a random variable x and a set of possible outcomes ki, our first rule is that the sum of the probabilities of all possible outcomes is equal to 1. While this is notationally confusing, this just makes sure that our listed possibilities completely describe the outcomes of an event. If the sum over all the possible probabilities were greater than 1, we could be more than 100% certain that something would happen, which is not possible. Moreover, if they were less than 1, we could not have accounted for all the possible outcomes and thus need to double check our model. Second, for each possible value of k, the probability that the random variable is equal to k sub I is an element of the interval between 0 and 1. Together, these 2 rules make sure that we can do more complicated math on random variables without breaking the rules of probability. This is particularly helpful to remember when dealing with the probabilities of several outcomes, which are referred to as cumulative outcomes. Sometimes we want to talk about the possibility of a range of outcomes, say the possibility that we roll 3 or smaller when we have a 6-sided die. We can write that our possible outcomes k are equal to the set 1, 2, 3, 4, 5, and 6. From here, the probability of rolling 3 or less can be written as the probability of x less than or equal to 3. This just represents the accumulated sum over the probability of rolling 1, 2, and 3. Together, our 2 probability rules will make sure that the result of this sum is less than 1, because rolling 3 or less is a subset of the possible outcomes. This sort of cumulative notation is very helpful when we are describing cumulative probabilities, and it works because all discrete event probability distribution functions are defined to ensure that we do not violate the rules of probability. A cumulative distribution function provides probability outcomes up to a certain value. More complicated constructions can be used to select a certain interval or the probability that the outcome is greater than some value. Let's use our die roll to see an example of a PDF and a CDF for a discrete random variable. Given a fair die, the probability distribution function of the random variable associated with the result of the die roll is going to be a uniform random variable. That is, the probability of any single outcome is equal to any other, in our case 1/6. We could graph this visually with a bar chart where the height is equal to 1/6, or about 0.166 for each outcome, and the x-axis provides the value of the roll. The cumulative distribution function, however, would require us to sum up the values smaller than each k. Before we do this, what do you think the value for the probability of k equals 1 would be, for k equals 6? Which rules can help you answer this question? Let's start answering this question with the probability that x is less than or equal to 1. The only outcome that satisfies this condition is the x equal to 1, so we have simply that the cumulative probability of x being less than or equal to 1 is the probability that x is equal to 1, or 1/6. With p of x less than or equal to 6, we can do this two ways. First, we could theoretically sum up the probabilities that each outcome is less than 6, giving us the probability of x equal to 1 plus the probability of x equal to 2, so on and on up to 6. This, of course, is possible, and we'll just see us adding fractions. However, we can notice that the outcome here is the same thing as the sum over all the possible outcomes. And by rule 1, we know that this is just equal to the total value of the probability, or 1. We can summarize the PDF and CDF for this random variable in the following table. Notice how the CDF is strictly increasing and sums to 1 once we reach all the possible values. More complicated random variables will have functional forms of this sort of table. This lesson began with a general discussion of random variables. We then moved on to discussing discrete random variables, their notations, and the type of events they describe. Finally, we discussed the properties of discrete random variables and introduced the concept of their probability distribution functions and their cumulative distribution functions. Overall, this video has just been a brief introduction to discrete random variables. For more examples and specific forms of these discrete variables, I encourage you to keep learning about them in various other places on Chegg.